Uh, Thank you, Alex, for this kind of introduction, and good morning to everyone in the UK, and good afternoon. No, good afternoon to everyone in the UK. Good morning to everyone in the US. Um, Indeed, as Alex indicated, I'm interested in the self-organization of materials and how these reactions can be used to design materials that are resistant to damage in service conditions. And in this particular presentation, I'll be looking at materials for demanding wear-resistant applications. The work that I'm going to present has been done in part at Illinois over the years by several graduate students and postdoc researchers, in particular Dr. Fusen Rang and Radhakrishnan Manavan. Um, Also, I've collaborated extensively with two of my colleagues at Illinois, Professor Shen Dillon and Bob Haverback, and you'll see the names throughout the presentation. And we collaborate as well with Professor Ashkenazi from Hebrew University and Horst Hahn from Karlsruhe Institute of Technology. And so briefly, the outline of my presentation, I will first start with some general consideration about how we select or design materials for high wear resistance. Second, I will discuss or present the self-organization of microstructures in alloys that are subjected to severe plastic deformation. Then we'll follow in the third point with looking at how the self-organization process or reaction can take place during sliding wear. And we'll, in the fourth point, look at microscopic testing to further improve our understanding of these self-organization reactions, and I'll briefly conclude. So first, I will start here with this point on the materials for high wear resistance. And we had an excellent webinar last month from Professor Alan Matthews, and so I'm reiterating on the slide briefly some of the points he developed last month. We know that wear is a complex phenomenon, in part because there exist many different types of wear processes of wear. Some of them are listed or depicted here on the left side of the slide. In these different processes, wear types, there are multiple physical, chemical processes that are relevant and dictating the evolution of these materials, and so it is a challenging environment and evolution of materials. Nevertheless, typically there are some general principles that are used to reduce wear. First one here is to lower friction, for instance, using lubricants and coatings. A second possibility or criterion that is often used is to increase hardness. But as Alan showed us last month, it's even probably better to improve the ratio of the hardness to the elastic modulus. And I taken this graph here on the right-hand side to illustrate this point, where some titanium, aluminum, boronitride coatings have excellent wear resistance, and in particular, you see that the coatings 5 and 6 have remarkable wear resistance, very low wear rate, and these are the ones for which this ratio of hardness to elastic modulus is the lowest. I'm sorry, the highest. These are the numbers you see in blue. And the third approach is to possibly promote self-lubrication by reducing chemical affinity so as to minimize chemical transfer across junctions. And this is an approach that's been promoted by Rabinovich, for instance, in the 70s. And so the difficulty, however, is that a pair of materials that are in contact and in relative motion with one another, so I would say it's a tribosystems, that these tribosystems are non-equilibrium systems or material systems, and they have certain key aspects that are important for what we're going to see. First is we'll see time-dependent evolutions with transient. So for instance, here on the right-hand side, you have um, a wear depth as a function of time for a particular pin on disk wear test. And you see on the black curve that there's an initial transient that may last for here about 15, 20 minutes. And after that time, the wear depth increases linearly with time. So we have reached a steady state. However, it is well documented that if we vary the conditions under which we perform the test, this steady state wear rate may change. In fact, Ashby and his co-workers, for instance, developed this concept of wear maps, where here we see different regimes for wear of steel on steel, and as you cross this thick line boundaries here, you may go from one type of wear to another, and so these boundaries are not always known ahead of time, and so it is difficult and challenging to design wear-resistant materials because by changing operating conditions, you may change the operating point of the material from one field, one domain to another. The third point here is that tribal systems may be sensitive to initial conditions. So we'll illustrate this point further in the talk. But one practical aspect that is relatively well known is the effect of roughness, for instance. And another point that you see on the graph on the top right corner is also changing the environment. Here, going from air to argon, or changing the sliding velocity in green can change the wear rate, the amount of noise or fluctuations that we see on the response of the material. Furthermore, we may start with a pair of bodies in sliding contact, but very often at the interface between this contacting asperities of the two first bodies, something else will be formed. This something else is what is often referred to as the third body, or tribal film, or tribal layer. And there are many conditions where the wear response or wear behavior is largely dictated by what's happening in this third body. And so suddenly it is, all these aspects make it difficult to predict wear resistance. And so on the next few slides, I want to illustrate these dynamical properties by looking first at what can happen at the wear surface, and then we'll look below the wear surface. So at the wear surface, for instance, we're talking about the formation of tribal film. It is well known that additives such as ZDDP can promote wear resistance. It is, and progressively over the last 5-6 decades, the community has developed a good understanding of the origin of this anti-wear property, and it is through the formation of glassy, patchy tribal films that screen or separate the two bodies and reduces drastically wear. And on the point number 2 here, recent work from Karpik and co-workers showed that the formation of this tribal film is activated by stress and temperature. So they use AFM studies here to show in varying the contact pressure that in order to form these patchy films that have the right anti-wear resistance, you need to be in a wear environment, and so these films are dynamical films that exist only during wear itself. More recently, and it's point number 3 here, it has been shown by Erdemir and co-workers that in fact coatings can be designed so as to promote the formation of this tribal film. So now you can control the formation of the tribal film not through an additive that's added to a lubricant, but by designing a coating that promotes the formation of the right tribal film. Here, copper or nickel are incorporated in a molybdenum nitride coating so as to promote the formation of a diamond-like carbon tribal film at the interface. And what you see at the bottom left corner is that for this ball on flat test, there is essentially no wear, even much less compared to the picture on the right, which is with a ZTDP additive. So what happens at the wear surface is important. Below the wear surface, there are also important processes, and these are the ones that we're going to focus on today. And in particular, for metallic materials, which is our focus here, plastic deformation is going to be very important. I've taken this picture here from a textbook by Hutchins about the evolution of microstructure, or typical evolution of microstructures in metallic materials subjected to sliding wear. So the wear surface is depicted here with this red dotted line, and what one sees is that typically the strain increases exponentially as one go from the bulk and approaches the wear surface. This increase in plastic strain has many consequences. So we'll see dislocation, accumulation, grain refinement, and even grain rotation as we approach the wear surface, say going from the zone 1 to zone 2. At the wear surface, and this is what we see on the right-hand side, we may even observe the formation of nanocrystalline layers. This is this layer labeled A from the work of Rigney and co-workers. Overall, this plastic deformation increases the hardness of the wear surface, which is possibly useful, but at the same time also it reduces the amount of damage that the surface can take before it fails. And so usually, even though this hardening might be beneficial, after a while this region will break up and fall off and be absorbed and become be ejected, and from the contact it become wear debris. And so the question that I want to address today is, can we use severe plastic deformation to our advantage? Yeah, it seems that it is problematic, but I would like to consider the fact that it might be beneficial. And so before we do that, I want to briefly review or discuss with you the fact that alloys and alloy microstructures subjected to severe plastic deformation can spontaneously self-organize. And I started here with a couple of examples on the next slide to illustrate that self-organization is observed in many non-equilibrium material systems, from oxidation. You see the formation of this layers of oxide here, to de-alloying, where using electrochemical means we can remove a less noble element from a matrix, leaving behind here a porous plug, which might be interesting for catalytic applications or filtering different molecules and particles. And on the right-hand side also, it's another situation where here in this case where one is driving the material away from equilibrium by irradiation, and that results in the formation of this well-organized lattice of voids, but at a length scale that's larger than the crystallographic underlying lattice of here niobium in this case. And so these self-organization reactions can be detrimental. This layering in corrosion is not good. It leads to a fairly fast oxidation rate by re-exposing the bare metal to the oxidizing environment. Another example is the well-known white etching layer on the surface of rails. But in some cases, self-organization could be useful. For instance, in de-alloying, as I indicated, you can control the size of the pores, and so that can be useful for filtering applications, and also it may provide materials with very high specific surface area, which can be good for catalytic applications. So, so the challenge that we are considering today is whether we could use plastic deformation, in particular the one triggered or induced by wear, to trigger self-organization reactions, and reactions that would be beneficial to to the wear response itself. So for this, we're going to consider simple binary systems such as copper-silver. So I grab the equilibrium phase diagram of the system. You recognize here a simple eutectic phase diagram. So, and we're going to work at low temperature, so near room temperature, a little bit above. So we'll be in this region of the eutectic phase diagram where the system should separate into two phases, one that is essentially pure silver and one that is essentially pure copper. These two phases are nearly pure phases are face-centered cubic. And when we're going to subject this system to plastic deformation, because of the similarity of the properties of copper and silver, particularly they're similar, not to different lattice parameter and elastic properties, they will co-deform. And so during plastic deformation, what we are going to see is that this co-deformation can force the mixing of copper and silver. On the other hand, plastic deformation also creates defects, include dislocations, but as point defects as well, vacancies. And so plastic deformation can be used to accelerate thermally driven kinetics. And I will illustrate this one more carefully on the next 3 slides or so. And so the first take-home message here is that depending upon the temperature and the strain rate, deformation can take alloys closer to equilibrium by accelerating their kinetics, or it can take them farther away from equilibrium by through this forced chemical mixing. And so to illustrate this point here, I reproduced some results obtained by Bob Averbeck and one of his collaborators, Thomas Classen, where you see different X-ray diffraction traces here of copper-silver that has been ball milled for a long time. So ball milling is one common method to apply severe plastic deformation to materials, and so we've used it quite a bit over the years in our laboratory. And so what is observed here is that from these X-ray diffractograms is that after long milling times, say a day, or alloys tend to reach steady state. So it's similar to the steady state wear rates we were discussing before. The steady state, however, is a function of the milling temperature. If we start with the top diffractogram here, or X-ray spectrum, you see only, or some of you may recognize that these are the typical Bragg peaks or reflections you expect for one FCC phase, with the 111 reflection here and 200 here. And so even though, as I said before, copper and silver should form two distinct FCC phases, here, by ball milling at low temperature, we forced the full mixing of copper and silver. And so it's an illustration of the power of this forced chemical mixing to homogenize here a composite or a two-phase material. As one increases the milling temperature, we go from the top curve to near the bottom curve, we see that there are additional phases that now are present, particularly if I focus on the bottom X-ray spectrum. Here one can show that this is composed of two FCC sets of Bragg peaks corresponding to a phase coexistence of a copper-rich and a silver-rich phase, and this is by milling at about 200 degrees Celsius. So here we go at the top in the regime from where deformation is driving the system far from equilibrium into solid solution, to the case where here it seems that the system is closer to its equilibrium state in the sense that it is decomposed into two phases. What we see is that in the middle there are some complex phase coexistence, but this is difficult to analyze just from X-ray diffraction. And to further improve our understanding of these processes, what we have done with Bob Averbeck is to use simple atomistic simulations to better understand what may happen or could happen in a system such as copper-silver. So here we take a system that wants to phase separate, comprised of blue and red atoms. And in this system, so we're going to work in a region of the phase diagram where at equilibrium it would phase separate. And this phase separation in the simulation is promoted by vacancy diffusion. And what we're going to do is, on top of this thermal diffusion, superimpose shearing as it would result from the glide of dislocations through this material. From now here, this shearing is going to be randomly taking place randomly in any of the 4 111 planes of the FCC structure, in along any of the 3 or 6 110 directions in one given 111 plane. The only thing we're going to set or impose is the shear strain rate, or the shear rate here. And so here we have these pictures represent one 111 plane in in this 3-dimensional FCC lattice. And here we start with this bilayer state, which is representative of the equilibrium state of the system at this temperature in the absence of plastic deformation. And we're going to observe what happens when we shear this material at low temperature or at a high strain rate. And so now we're starting this short movie, and you see that there are different processes that are taking place, but quickly the initial interface became blurred, in part by the roughening of the interface and by this forced mixing. And so now, after some time, we have reached a microstructure that is essentially random. And this is very similar to what we were looking at when we ball mill copper and silver at liquid nitrogen temperature, in the sense that in that case, thermal diffusion is very sluggish and deformation dominates the evolution of the material. If we had started with a random state, which is the movie on the right here, well, since we are imposing random shearing, we expect this random state to remain stable, and this is what you see again in that movie. And so here in this case, at high strain rate, or equivalently at low temperature, this two-phase system, or phase separating system, reaches a steady state, which is a solid solution. And it's remarkable already because this state thermally would be unstable, and yet it is the stable, steady state of the system when it's subjected to high strain rate deformation. Let's, in the second case, now consider a situation where the strain rate is low and compared to thermal diffusion. And what we see is that that same bilayer now is evolving much more gently. There is a little bit of roughening of the interface. Some steps are formed, but you can see that essentially the two-phase coexistence is preserved during shearing or during deformation. And on the right-hand side here, starting from a solid solution, now we see that the system forms two phases, and slowly it will it will evolve and reach the same steady state as the one depicted on the right. That is, again, we have a unique steady state here. The simulation didn't run long enough, but in this particular case, however, the steady state is one where we have macroscopic phase separation between the blue phase and the red phase. And it's reminiscent of this macroscopic phase separation in copper-silver mixtures ball milled at elevated temperature. So the third case is the more interesting, is where now we are shearing this copper-silver alloy or blue-red alloy, and under conditions where the strain rate and the thermal diffusion are of similar strength. And now starting again with this bilayer, what we see is something different. Again, interfaces become rough, but this roughness keeps building up and results in the formation of some ramification of the structure or refinement of the microstructure. And progressively we are forming a nanocomposite. And if I start from the random solution, this is on the right-hand side, you see that now we have the system starts by forming regions that are copper rich and silver rich, or red and blue. But the remarkable point is that this phase separation never reaches the microscopic scale. And so here, after a while, we would see that these two systems reach the same or statistically equivalent steady state. These steady states are like a two-phase system, but they have a finite length scale, so we refer to them as compositional patterns. What we observed here is that this system has self-selected the length scale of this phase coexistence. And if we were to vary the strain rate or the temperature, we can continuously tune or change the length scale of these nanocomposites. And so in this particular case, the steady states are independent of the initial microstructure. This is what we have just seen by watching these two movies. There's another point that's interesting already to notice, is that in some way these structures are self-repairing, because if we were to change temporarily the temperature or the strain rate, you'd see that the system might evolve dynamically, and then as you would return to a lower temperature or the initial temperature, the structure would readjust to the original operating conditions. And so in some ways, these structures, since they evolve dynamically, can somewhat repair themselves from imperfections or transients. And so this slide here, the next slide, summarizes essentially these three different steady states, where the microscopic phase separation on the left, the solid solution on the right, and these mesoscopic two-phase system in the middle. And so the next two questions that I would like to address is, one is, do these compositional patterns form experimentally? And could we use these patterning reactions in a useful manner for wear applications? And so the main point is that really I put check marks on these left and right steady states, because as I showed you before, from X-ray diffraction, we know that these were the steady states observed during ball milling of copper silver at very low temperature, at elevated temperature. So what we did naturally is to ball mill copper silver at intermediate temperatures and look at this by TEM. So on the left-hand side, you have a schematic drawing of this powders being ball milled. That here, the milling took place at about 230 degrees Celsius, which is at the temperature where thermal diffusion in copper silver becomes significant. And on the right-hand side, you have chemical map obtained from scanning transmission electron microscopy, where copper-rich regions show up as purple or blue, and silver-rich regions as green. And you can see that indeed here we have a nanocomposites that are very similar to the one we observed in the atomistic simulations I showed you in a couple previous slides. And so it seems that the self-organization reaction do take place experimentally. The question that's somewhat puzzling, puzzled us for a while is, and it's the case in many of these self-organization reactions, is that what is the origin of the length scale selection? So how does the material know which scale or length scale to select? And we said that this nanocomposite results from a competition between thermal diffusion and plastic deformation. Transport and mixing through thermal diffusion is well understood. This is the classical theory of diffusion in materials, in crystalline materials in particular. So this we understand very well. So what we realized is that a key point in understanding the origin of this length scale selection was to look at the mixing that's forced by plastic deformation. And here it's interesting to make an analogy with convective flows. On the left-hand side of taking a cross-section of a particle of copper silver that is being ball milled, but stopping before one has formed a solid solution or nanocomposite. And you see these stretched fibers or platelets of copper and silver. And this is somewhat reminiscent of how materials would flow in the liquid. So for instance here, for just there's no deeper point behind this comparison, but just saying that visually this looks very similar to the transport of here a drop of ink in turbulent water. In fact, when we want to evaluate the mixing of chemical species on the left, with Bob Averback, we developed an approach that helped us to understand this question of length scale selection. And we learned after the fact that this is the approach that has been also developed for studying mixing in convective or turbulent flows, in following the work of Richardson almost now like 80 years ago. And this approach relies on the following ideas: that if you were to follow one point, the evolution of one marker, say an atom 1 here in red, this point may undergo a random motion, and it would be hard to obtain some useful information from the random motion of this marker number 1. Now, it is, however, very useful to consider the evolution of the separation distance between different markers. So here, for instance, I could consider two markers, 1 and 2, so a pair of markers, and monitor their relative, the evolution of their relative separation distance. And this relative separation distance is a good measure or useful measure of how mixing proceeds in the systems. And you can see that now, if I consider the case of materials subjected to plastic deformation, well, the initial separation distance matters, because if I take pairs of markers, say 2 and 3, that are farther apart, in the case of homogeneous plastic deformation, for simplicity, the number of dislocations that are going to shear this pair of atoms, the 2 and 3, is going to be proportional roughly to the separation distance. So the farther the pairs are apart, the more often dislocations shear them, and each time a dislocation shears this pair here, it displaces them by 1 Burgers vector, so increasing or modifying the separation distance. And so what Richardson proposed is to define an effective diffusion coefficient that is a function of the pair separation distance. And in this particular case, one can show that it's this effective diffusion coefficient is proportional to the pair separation distance, the Burgers vectors of the dislocations involved in plastic deformation, and the average homogeneous plastic strain rate. And so this mixing is referred to as super diffusive. That is, it takes place faster than diffusion. And you can see in particular that if we have pairs that are far apart, this mixing is faster. So there is a dependence of the mixing with length scale. One prediction from this super diffusive mixing is that if I had a precipitate here in the middle, the strain it would take to dissolve this precipitate scales linearly with the radius of the precipitate. And we tested this prediction by preparing materials with different silver precipitate size in copper, and so the red and blue squares are results from experiments, and the line is the fit through this equation here and up to a coefficient, a geometrical coefficient. We see that there is a very good agreement with this idea of super diffusive mixing. So the important point is that now, if we were to go back to the situation where there's a competition between the mixing forced by plastic deformation and phase separation promoted by thermodynamic forces, which is this diagram here on the left side, the effective diffusion coefficient for induced by shear increases with the pair separation distance r, whereas thermal diffusion in red here is independent of this pair separation distance. And so you can see that the outcome of this competition becomes scale dependent. In this particular case, at short scale, thermal diffusion is more effective than the forced mixing, and so we expect the system to be decomposed. At larger scale, however, the mixing forced by plastic deformation is more effective, and so we expect the material to be homogeneous at that scale. And there is, and so a natural prediction idea is that the crossover between these two response curves here is the scale at which the patterns are stable. And so it gives us a guideline as to how the length scale of the patterns would change with diffusion and plastic strain rate. In particular, if I were to increase the temperature from T1 to T2, the red line would move to this dotted red line, and the length scale of the pattern should shift from this value to a larger value. And we tested this experimentally, and that's what you see in the bottom, where we have microstructures in 3D here of copper and silver powders that have been ball milled at slightly increasing temperature. And you can see that progressively in these steady states microstructures, we see increased phase separation and also an increase in the length scale of the phase separation. So here we talked about self-organization so far of alloys. There is another complication to this picture, which is that when we plastically deform materials, depending upon the conditions we impose, we'll have different types of strain path or stress conditions. Ball milling typically, for instance, generates triaxial stresses. Wear generates or can be approximated by simple shear deformation, rolling with the plane strain. And it is known that in response to this plastic deformation, pure metals may self-organize as a result of self-organization of dislocations. So here you see on the left an example of layered structures that formed in pure copper during sliding wear, but dislocation cells and subgrains forming in tension. And so the question now is, what would happen to alloys subjected to severe plastic deformation? Would they be dependent upon the strain path? And so this is now what the main point that we're going to cover in the next 5 minutes or so is to consider this self-organization reaction during sliding wear. So staying again with this copper-silver system, we ball mill, we make powders, we compact the powders and sinter them at intermediate temperature. And what then we do is we tune the size of the silver precipitate by annealing at different temperatures. And in this particular case, we have a prepared copper-silver composite with here 10% silver and copper, with precipitate sizes ranging from about 30 nanometers to about 300 nanometers. And then we use a pin-on-disc test to see how this copper-silver composite performed for different precipitate sizes. And on the next slide, I have a stem micrographs of the initial microstructure of this composite. So on the left side, you have one that has been annealed at low temperature, the silver precipitates, which are in these white regions here, are small compared to an annealing at a higher temperature here, where the silver precipitates are about 300 nanometers. As expected, this material here is softer. Its hardness is only 2.5 gigapascals compared to about 4.5 gigapascal on the left. And so if we were to follow traditional guidelines for designing wear-resistant materials, let's see, for instance, from Orchard, or we would expect the material on the left to perform better. But when we perform these wear tests, what we observed is, so the wear response, which are the red and green curve here, varied as a function of the precipitate size, which is, you can read at the top, but in a way that goes against the prediction from Orchard's law. So in particular, the precipitates that are the largest, so here on the right side of this graph, are the ones that have the lowest wear rate. So the red and green curve reach the lowest value. But at the same time, so these are materials for which the hardness, sorry, in green here, is the lowest. And so here this material has the best wear resistance, despite the fact that it does not have the highest hardness. And so we looked at the microstructure of these materials to understand why this may have happened. Here's a cross-section of this material. The yellow dashed line is the wear surface. And what we see is that far from the wear surface, we have silver precipitate. then they start to be stretched because of the action of plastic deformation, and progressively we form a solid solution, which is here an indication that the forced chemical mixing is so effective that it dissolves these precipitates. This is for small precipitates. However, when we started with a microstructure that is initially large precipitates, we see a totally different microstructure, and near the wear surface here, we observe the formation of nanolayers, alternating nanolayers of silver in bright and copper in dark. And you can see that these layers can become very thin, and this is the microstructure that is the best wear resistance. So in fact, here we have a panel of TEM and STEM micrographs. So on the left, it's more like the structural characterization of the microstructure. On the right, the middle column, it's more the chemistry. And here we're looking down away from the wear surface. We see that this nanolayering extends over several microns. And as we go deeper and deeper into the material, it is interesting and useful because essentially we are looking at this nanolayering reaction at earlier and earlier times, in the sense that the strain that has been applied here is small, and so the layering reaction is not fully at the full time to complete, and this layering takes place here along the sliding direction, but also across along the transverse direction, as illustrated on this picture on the right. And so we are tested also that this nanolayering reaction can take place under other type of severe plastic deformation here under pressure torsion, where again simple shear deformation dominates. And so in order to better or quickly understand this the formation of this layering reaction, we can go back to the model that I had before, but now bias the plastic deformation so that we'll have deformation predominantly in one of the four 1-1-1 slip planes, so as to mimic this simple shear deformation. And if we do that, starting from a solid solution, you see that for conditions where a nanocomposite would form, we do see a nanocomposite, but unlike the previous case where it was isotropic, here over time, this nanocomposite it evolves as more like a nanolayered system, and this is a 3D observation of this nanolayered structure. So it helps us a little bit to understand how nanolayering can take place, but it's somewhat simplistic because it ignores interactions between dislocations in alloying elements. Here there are no grain boundaries, and grain boundaries play an important role. And so we have also used molecular dynamics simulation to have a more realistic understanding of this nanolayering reaction. And we do see here the stretching of this silver ball in yellow in response to simple shear deformation and formation of layers, and it also illustrates the role of grain boundaries, that they can guide the extrusion of the softer phase here, silver. So one point of that I think is important to appreciate is that so these non-equilibrium systems can reach different steady states, and but the steady states are not necessarily all the same. So doing ball milling on the left-hand side, and what happens is that we prepare the system by setting the temperature, the plastic strain rate, and what we do is we let it evolve for an infinite amount of time, or for an infinite amount of strain, and reaches a steady state, which may be this layered structure. And often what is found, and this is the case both here in the simulation and the experiments, we found that the steady state is independent of the initial state. However, what I just showed you is that for sliding wear, by changing the size of the silver precipitate, we get different wear response. But this can be understood or better appreciated by realizing that here we have a different type of systems where we have a moving frame of reference. So because this material is rising to the wear surface, and at some point is being removed and transferred to wear debris. And so the steady state wear response is one where these material or pieces or volumes have not been exposed to an infinite amount of strain by a finite amount of strain. So, um, uh, the possible benefits of this nanolayering we've considered them, and in particular, uh, we know that it's not due to reduction in friction. We shown that through other tests that nanolayers can localize plastic deformation at interfaces, and this is what you see here in this nanolayer tested in situ in a transmission electron microscope. And this nanolayer structure is in fact reminiscent to some extent of the nanolaminates or that Alan Matthews mentioned in his webinar last month, or this Roman paved road, if you remember, where there are hard inclusions cemented together by a softer and more compliant phase, and this should promote fracture toughness. These tests, however, or this understanding is, as you can see here, is easier to achieve by performing microscopic testing. And so briefly in the remaining 3-4 minutes, I'd like to illustrate quickly some of the results that we have obtained at Illinois using microscopic testing. So instead of letting a system here to develop multilayers, we would grow multilayers by physical vapor deposition. So here you see your copper silver multilayer. Then we use a tribo indenter to scratch a patch on the surface of these multilayers. We can image this by AFM to measure the wear rate, and also use FIB and TEM to measure or observe the microstructure just below this wear surface. The main goal being to determine the role of layer thickness on wear resistance here at the microscopic scale. And what we found is similar or reminiscent to our results on microscopic tests. So on the left-hand side graph, this is the wear rate for various multilayers. All of them have the same average composition. And the lowest wear rate here is obtained for the thinnest multilayers, where we have multilayers with alternating 12 nanometers of copper layers and 2 nanometers thick silver layers. And this wear resistance is the best here. When we look at the microstructure in cross-section by TEM, we see that the multilayers are still present, but close to the surface, the plastic deformation has forced the formation of a copper-silver solid solution. Nevertheless, these multilayers provide better wear resistance, because if we start with the solid solution to begin with, the wear resistance is higher. This is the red dashed line here. And so this microscopic testing helps us to understand, illustrate the fact that interfaces, chemical interfaces, do promote wear resistance. And so not all layers, however, are equal, and so there's a work that I borrowed from the literature showing that thicker layers here of copper and gold may behave or respond differently. And so in this case here, you see the evolution of layers that are more like 100 nanometer thick, and the response is different, and they develop instabilities that are possibly driven by a Kelvin-Helmholtz instability that is also reminiscent of reactions that are seen in rock formation. And these instabilities, in fact, have been reported and seen quite a while ago in the literature. And I borrowed this picture from a paper by Namsu from the mid-70s, already showing unstable mixing at interfaces under sliding wear. So, in summary, I think the key points are organized in these three blue bullet points. I believe I showed you that plastic deformation can stabilize self-organized microstructures in alloys. If we have triaxial stress or strain, these nanostructures tend to be equiax, so it's maybe reminiscent of the salad dressing that you obtain by stirring oil and vinegar On the other hand, if the plastic deformation that's imposed is has a directionality to it, which is the case during sliding wear, where we have simple shear, the resulting micro or nanocomposites tend to form nanolayers, and this is maybe similar to croissant dough, and as we all know, we prefer croissants over salad dressing, so this is better. And so most seriously, what we found is that this nanolayering significantly improves the wear resistance, that the thinner the layer, the better, probably by promoting strain localization and crack deflection. And the more broader point here in conclusion is that self-organization provides an adaptation for these materials in operando, that is in service. It improves wear resistance where it's needed. And it is only interesting and challenging to design materials and integrate this with other criteria that are used for material design. So we might say, how can we design a material that would be good for wear resistance and for corrosion resistance? But I want to also leave you with the point that the idea that these self-organization reactions are used in other environments, and for instance, at Illinois with Bob Everback and Shan Dillon, we are using these self-organized reactions to design radiation-resistant materials for nuclear applications. So thank you very much for your attention. I would be happy to answer